Okay, so today we'll continue with this Fourier series analysis method and the Fourier series. Integral. The purpose is to find our Fourier coefficients. The Fourier series coefficients. Fourier series coefficients. The formula goes like this. To compute the coefficient at the kth harmonic, you take the Fourier series coefficient by taking the signal, multiplying by the negative kth harmonic, integrating over one period, and dividing by the period. This integral formula is Fourier series analysis. You should really view this formula in two parts. This is the case where k not equal to 0. If k equals 0, you can plug k equals 0 in. This term becomes 1, so a0 equals 1 over t0 times the integral over one period. That's k equals 0 plugged in. So this is the k equals 0 case. It's still one formula, it's just that. When computing it, you need to be careful and treat k equals 0 and k not equal to 0 separately. And the k equals 0 result is what we call the DC component. EC means the component, meaning when k equals 0. That's the DC component. When k not equal to 0, it's not DC. Okay, another point. Suppose x of t is real. Meaning it's real valued. If x of t is real valued, then we have a property. The coefficient at the kth harmonic. In the Fourier series. And the coefficient at the negative kth harmonic. In the Fourier series are complex conjugates of each other. This is easy to prove. Let's take this expression and look at it. If I take the complex conjugate of AK, the complex conjugate of AK, since an integral is just a sum. If x of t is real valued, the only negative is in the exponent, so the conjugate flips negative j to plus j, giving 1 over t times the integral over one period. And a spaced k with negative k. Replace k with negative k. Replace k with negative k. See it? Isn't the conjugate of AK equal to A minus K? But note, this only holds when x of t is real valued. That's something to keep in mind. In most applications, x of t is real valued. So your Fourier series coefficients are very often complex conjugates at positive and negative frequencies. We did examples earlier where the positive and negative frequencies are complex conjugates. As long as the signal is real valued, it holds. Alright, next let's practice with an example. We'll use a square wave, a signal x of t. Here's the example. It's either 1 or 0. From 0 to t0 over 2. The signal equals 1, and when t is from t0 over 2 to t0, it equals 0. Drawn out, it looks like this. It's a periodic signal. The problem says t0 equals 0.04 seconds. So, from 0 to 0.02, it's 1. Then from 0.02 to 0.04, it's 0. Then it jumps back up. Same here. Minus 0.02. Now I give you this square wave. And I want you to tell me what sinusoidal waves it's composed of. Notice, this square wave is periodic, so we can analyze it with a Fourier series. So I'm giving you a periodic square wave. Now you can use a Fourier series to analyze it. First, remember, we compute two things, the DC term and the non-DC terms. The simplest way is to find k equals 0 first. A sub 0, the DC component. It's the integral over one period, divided by the period, and the period is 0.04. So we integrate from 0 to 0.04. 0.04. Integrate from 0 to 0.04. And then this is x of t. Then we multiply by the 0th harmonic, which means we don't multiply by anything. So it's essentially 1 over 0.04 times the integral from 0 to 0.02, since only 0 to 0.02 is non-zero, dt. The answer is 1/2. So the DC term is 1 over 2. Next, for k not equal to 0, A sub k is 1 over t0 times the integral over one period. It's 0 to 0.04, but only 0 to 0.02 has a value. So we integrate from 0 to 0.02. Here, x of t equals 1, multiplied by e to the power of negative j k omega naught t. For the k harmonic, what's the fundamental frequency? The fundamental angular frequency is 2 pi divided by t naught, so 2 pi divided by 0.04. That term is omega 0. So omega 0 equals 2 pi divided by t0. Multiply by t, then dt. Next, after integrating, we get 1 over 0.04 times the reciprocal, which is 1 divided by, open parenthesis, negative j k 2 pi over 0.04, close parenthesis, comma, period, times e to the power of negative j k 2 pi divided by 0.04 times t. E to the power of negative j k 2 pi divided by 0.04 times t. Evaluated from 0 to 0.02, these terms cancel. Plug in 0.02. Point. Set t equals 0.02. 0.02 over 0.04 is 1/2. And the 2 cancels, so the answer becomes 1 over negative j 2 pi times, with t equals 0.02. Point. Since 0.02 divided by 0.04 is 1 over 2. So you get e to the power of negative j pi. At t equals 0, this term is 1, so subtract 1. Okay. What is e raised to the power of negative j k pi? What is e to the power of negative j k pi? Pi is 180 degrees. So, with 2 pi, when k equals 0, the term is 1. But when k equals 1, ... This is e to the power of negative j pi, i.e., negative 180 degrees, and this becomes minus 1. So it becomes either 1 or minus 1. Or you can factor it as e to the power of negative j pi to the k power. Think of it as raising it to the k. So, it's easier since e to the power of negative j pi equals negative 1. You can treat this as open parenthesis negative 1 close parenthesis to the power of k. Then we can simplify it to bringing the minus sign in, giving 1 over j 2 pi k, and then multiplying by negative 1 gives 1 minus negative 1 to the power of k. Since e to the power of negative j pi is negative 1 raised to the k, we get a few cases. One case is k equals 0. The answer is 1/2. For k is equal to 0, it's this expression, and we can simplify further. Why? Because when k is odd, (1 minus open parenthesis negative 1 close parenthesis equals 2). But when k is even, say k equals 2. Negative 1 to the power of 2 equals 1, so 1 minus 1 equals 0. So for odd k, it remains. For even k, it's different, so the result we just got is ak equals 1 over j2 pi k times 1 minus negative 1 to the power of k, and a0 equals 1/2. This is the cleaned up expression for k factorial equals 0. So a sub k has 3 cases. First, if k equals 0, it's 1/2. If k is odd, like plus minus 1, plus or minus 3, period. The odd integers. Then 1 minus negative 1 equals 2, and the 2 cancels. So it's 1 over open, j pi k close parenthesis. If k is even, like plus or minus 2. Plus or minus 4, then. Negative 1 to the even equals 1, so 1 minus 1 equals 0, so we get 3 results. Now we can draw the spectrum of this square wave. We can plot its spectrum. So, at frequency 0, the magnitude is 1/2. And when the frequency is an odd harmonic, like the first harmonic. Remember, T0 equals 0.04. So F0 is 25 Hertz. 1 divided by 0.04 is 25 Hertz. So at 25 Hertz, if the horizontal axis is F, there's a line there with magnitude. K equals 1, the first harmonic, A sub 1. The fundamental is 25 Hertz, so A sub 1 is at 25 Hertz. And it's 1 divided by j pi. We can simplify further. It's 1 divided by the pi times k times 1 divided by j. Multiply numerator and denominator by j, and you get, I'll write it out, j, which equals negative j. So it's a phase. The phase of minus j is minus 90 degrees. So when k equals 1, the magnitude is 1 over pi, and pi is about 3, so it's about 1/3. Roughly, we can sketch it like this. It's easier to write it as 1 over j pi k. No, wait, there's no k anymore, since k equals 1. Let's write k equals 1, semi. So it's 1 over pi, and the phase is negative pi over 2. If k equals 2, that's 50 Hertz. 50 Hertz is even, so it's 0. We don't plot it. If k equals 3, that's 75 hertz. 1 divided by open parenthesis 3 pi close parenthesis. And the phase is the same. K equals 4 has nothing. K equals 5 is 1 divided by open parenthesis 5 pi close parenthesis period. With the same phase, we can also plot k equals -1. It's 1 over pi in magnitude, with the exponential coefficient. Since here, k equals -1. So, when k equals -1, you carry the minus sign through, so the phase angle has magnitude 1 over pi, and there's a -1 here. Combine that -1 with the phase. Let me write it out. Multiply by -1. That -1, and here we have minus j times -1 is j. And j is what angle? 90 degrees. So it's j over pi. So a sub -1 is j over pi. Minus 25. -50 has nothing. Minus 75. Which equals? For k equals -3, it's 1 over 3 pi. Minus 100 has nothing. Minus 125 has a little. So we've plotted the spectrum. I won't plot the 7th harmonic and beyond. After all these complicated calculations, we use Fourier series analysis at the kth harmonic. Multiply the signal by a -k harmonic sinusoidal wave. Then integrate to find the square waves. Fourier series coefficients in the spectrum, we get them. And we can plot the Fourier series coefficients and what their spectrum looks like. So this process tells you that for any periodic function, as long as you plug it into the Fourier series analysis formula, you can compute its Fourier series coefficients. A square wave is interesting. It has DC. It has a DC component. Look at this square wave. It has DC because it's not positive and negative. It's all positive, so it must have DC. And that DC level is exactly 1/2. So, after we compute the spectrum, this term here is the DC part. This is the DC part. Okay. Finally, let's look at the overall workflow. We start with a square wave. Through Fourier analysis, we compute AK by integrating over one period and dividing by the period, multiplying by the -k harmonic, and we get AK. We get A sub k, and then for each harmonic, we use Fourier synthesis to reconstruct the original signal. That's the spectrum we started from. And you might ask, Professor, why does this reconstruction look a little different? Because there's a difference in synthesis. We didn't use the entire infinite spectrum. We didn't use the whole infinite spectrum. What does that mean? We just saw this. For a square wave, its frequency content. We ask whether its bandwidth is finite or infinite. If you plug into the formula, a square wave has infinite bandwidth, even for large k. For large k, there's still something, unless k goes to infinity. So there are frequency components all the way out, so it's not a band-limited signal. So when you synthesize it, during synthesis, if you only use a finite bandwidth from -n to n, not from -infinity to +infinity, then the reconstructed waveform uses only first, third, fifth, seventh, ninth, 11th, 13th harmonics. They get smaller, but they're still there. If you don't include them, the reconstruction naturally won't look as much like the original square wave. Now let's look at the synthesis result. What does the synthesized time domain signal look like? What does the signal look like? If we only use up to the third harmonic, meaning we keep only the first few harmonics, only up to the third, DC, then the first and third. We only use the spectral lines from 0 to the third harmonic. After synthesizing those 5 peaks, this and this combine into one cosine. Remember, those two are complex conjugates. Those 2 peaks combine into a cosine. Those 2 peaks also combine into a cosine. This one and this one. 25 Hz gives one cosine, 75 Hz gives another. Plus the DC term, those 3. After we synthesize them and plot it on a computer, the curve we get is the blue line. The original square wave from 0 to 0.02. The original square wave is the red line. The blue isn't the red, but notice, using only a few spectral lines, just a small spectrum, we can synthesize something very close to the original signal. The blue isn't equal to the red, but they're close. That's synthesis. And that's related to signal compression. Suppose we have a photo or a signal. Originally, to record this red signal, we need a lot of sample points to store that signal. But if we want to store the blue line on a computer, we don't need point-by-point samples. We just store the information for those 5 spectral lines. 0 Hz, 25 Hz, 75 Hz, and their corresponding amplitudes and phases. 1, 2, 3, 4, 5. 5 sinusoidal waves. Each has 3 parameters: amplitude, period, phase, and frequency. So that's 15 pieces of information. With that, we can reproduce the blue waveform. It's not the red one, but it's already very close. That's Fourier analysis in action as a form of compression. To store the red one, I'd need too many points. With the blue one, I store it as a formula. Now if we include up to the seventh harmonic. Up to the seventh harmonic. Up to the seventh harmonic. 1, 2, 3, 4, 5, 6, 7. Each pair can be combined into a cosine. Every pair makes one waveform. Then we write it as a formula and plot it on a computer. Plot the blue line. Compare using up to the third harmonic versus up to the seventh. The blue still isn't exactly the red, but it's even closer, right? Now if this were an image, originally it might be black, white, variations. Can your eyes detect that little wrinkle? Actually, you can't. That's compression. I can't store all the original information, but I store the blue information. Its formula. And the blue line is very close to the red line. If you apply this to image processing, the naked eye may not be able to see the difference between the blue line and the red line. If the signal goes high and low, and high represents white and low represents black. White, black, white, black. If there's a little ripple in the white region, can you tell? In fact, you really can't with the naked eye. That's the principle of data compression. So, you see, using up to the seventh harmonic gets even closer, using more. Up to the third, up to the seventh, up to the 17th, gets closer and closer to the original square wave. Of course, if we could go all the way to infinity, we'd recover the original square wave. But in practice, there's no infinity. ... We just try to approximate the original waveform. If you use this for image compression, this process is changing the compression ratio. If you use more and more Fourier series coefficients, then naturally, your data gets closer and closer to the original, but you need more information to store it. Conversely, if you use less information, you store less, but compared to the original waveform, the difference is larger. More data is better. Less data is worse. You trade off between the two. You might decide 7 is good enough. So you use 7 harmonics and compress the data a lot. Fourier analysis is exactly the same idea as JPEG compression in digital cameras. Okay, or MP3 compression. Why can MP3 compress so much, yet it still sounds about the same? It's the same idea. And of course, the more you store, the more beautiful the signal looks, but the larger the file size. So today, whether it's MP3, MPEG, or JPEG, we're not storing the raw information. In fact, we store their Fourier series coefficients. Later, you'll learn about the cosine transform, but the basic idea is the same. As we keep synthesizing, using 1 through 17, and we could use more. More and more, we'd get closer. But then Fourier analysis isn't very useful, right? For compression, if we store a lot, there's no point. So how many is enough? Well, of course, for a square wave, you'd need infinity. The original square wave has a very rapid transition here. What frequency content is that? It's infinite frequency. You can't use only low frequencies to synthesize that rapid. Transition region. That's impossible, because the frequency there is actually infinite. In other words, at an information discontinuity. When we do Fourier synthesis, we often see the signal exhibit overshoot. It should switch here, but it goes past it and then comes back. Because it's a discontinuity has infinite frequency, and you didn't use infinite frequencies in your synthesis, so naturally you get overshoot. We call this phenomenon the Gibbs phenomenon. The Gibbs phenomenon. It especially shows up at discontinuities in images. And not just images. Any discontinuity in a signal. In images, a black-white boundary. After compression. At the black-white boundary after compression. You'll see a little ripple here. An overshoot effect. That's called the Gibbs phenomenon. Gibbs is a person's name, okay? And that's one way to analyze Fourier series coefficients.